Okay, thanks so much for the invitation. It's actually the first time for me at KITP, and it's a great way to start again giving talk in person to a live audience. So my talk, I'll tell you a little bit about how we can use trapped ion to engineer spin system to study many-body physics. This is very broad. I'll cover 3 papers after a very short introduction about the main feature of the quantum hardware. I'll talk about prethermal time crystals, the observation that we have done very recently, we published. And I'll talk about a very recent experiment about stark SMBL that we observed also very recently. And then this is related to work that I've done in my previous group at JQI, in the group of Chris Monroe. And then I'll tell you a little bit about what we're doing at Rice, and in particular, I will cover this theory proposal about Floquet dissipative system and how to observe in a trapped ion setting measurement-induced phase transitions. So let me start from the beginning, basically from a video of how we actually assemble this quantum hardware atom by atom. So we usually work in a chain, and from this video you can see that, you know, the main advantage, one of the main advantages of ions is that they repel each other, so it's very easy to resolve them. It's very easy then to measure them individually and also to manipulate them individually. So when basically we cool them down in a Wigner crystal, well, never happened before, but okay, that's psychedelic. So when they actually arrange in a linear chain, the competition between Coulomb repulsion and the harmonic potential that we impose from the outside creates 2 second-order normal modes. And we've seen in the previous talk that this normal modes is actually how we create entanglement by coupling motion and spin. So this is related to the spin, to the motion, emotional degrees of freedom. But of course, if we have this beautiful ion chain and we want to study spin system, we need to isolate 2-level system. Luckily, atoms are one of the most anharmonic systems in nature, so it's very easy to find 2 levels that have very good coherence properties. Actually, in ytterbium, now this is the latest result. It gets better every year. The T2 has been measured to be 1 hour, so we don't have problems in terms of coherence time in the dark. We can prepare our initial state by effectively purifying through dissipation, and this will be also related to the last topic that I will cover today with optical pumping. And at the end of the experiment, we can discriminate between up and down by using spin-dependent fluorescence. So if we project up, we scatter many photons. If we project down, we scatter no photons. Of course, between preparation and detection, we also want to coherently manipulate the system, and we can do this with lasers, off-resonant lasers, very similarly to what Anna Maria was talking about. We use Raman beams, and we basically coherently couple spin and motion, or only the spin for 1 qubit gate, and we basically don't couple to the environment and create a unitary evolution. So basically, very quickly, the setting that I will be describing today, the experimental configuration, is 2 global Raman beams that address all the normal modes at the same time. And this is, Anna Maria gave a very good explanation of how, in her case, it was the cavity photon, but in this case it's very similar. It's actually the phonon, the collective modes that basically are emitted from one ion, and then they are absorbed by another ion, and this causes a correlated spin flip. And so this creates a pure spin-spin Hamiltonian if we integrate out the motional modes. That is inherit the long-range character of the Coulomb on the underlying Coulomb interaction. And interestingly, we can tune this alpha by changing the laser parameters, the laser detuning. Theoretically, this is from 0 to 3, but for practical limitations, we are bounded roughly to this range, depending on the system size. We can add also global fields along any directions. And most importantly, in this talk, I will describe how we use this localized, tightly focused beam to actually create side-dependent magnetic fields, or if you want to call it in another way, side-dependent rotation. So we can create arbitrary initial product states, and we can also create arbitrary potentials, one-body potential, for example, a gradient in the Stark MBL. All right, so so why this model, why long-range IC model is so interesting? Well, the main thing is that it breaks integrability. So short-range interacting spin systems are actually integrable, but if you have long-range coupling, then to compute when you perform a quantum quench, and that's what we do all the time in these experiments, it's actually very hard to compute the exact dynamics. And that's why these quantum simulators are so interesting right now. So there are these two reviews that covers different experimental and theoretical aspects of trapped ion quantum simulators and long-range systems in general. What we use in recent years, trapped ions have been used to basically observe quantum quench and thermalization, for example, or lack of thermalization in a closed quantum system. These are two papers that observed MBL with all the different caveats. Of course, it's a finite size system. We used recently in JQI trapped ions to study dynamical phase transitions, and we heard in the previous talk about that. And also we observed confinement domain walls of domain walls. And what I want to point out is that these systems are really on the brink of what you can do with numerics, with exact diagonalization. So that's why it's a very interesting place to be from the fundamental physics point of view. We can actually answer questions like, is there domain wall confinement, or how would the domain wall size probability behaves after a quantum quench in this dynamical phase transition experiment. So, all right, so we are going to use, in this talk, I'm going to talk about how we use this toolbox. Oh, please interrupt me if you have questions about anything. So we're going to use this toolbox to observe a prethermal Floquet discrete tank crystal. So in general, Floquet discrete tank crystal are kind of an extension of the space crystal, the one we're used to, that basically break via spontaneous symmetry breaking the continuous translational symmetry and create crystals. So for several no-go theorems, we cannot do the same with continuous time translational symmetry, but we can break discrete time symmetry. So if you have a Floquet system with a certain drive at discrete with a certain frequency, what we look for if we want to observe a time crystal, we look at robust, meaning that even if the perturbation is applied, that we still see this subharmonic response. A robust subharmonic response that is also stabilized. It's not fine-tuned. So it's robust and it's stabilized by many-body interactions. So I'll give a very naive characterization of how thermalizing system behaves in general in static and Floquet system. So for static system, we know that if the system is thermalizing and basically obey to the ETH, which means that each eigenstate is thermal. So if you take a portion of your system, the entanglement entropy will scale like the volume of the area, and also the reduced density matrix will look thermal. So the most notable example of how this can be avoided is MBL, where the entanglement entropy of each eigenstate is basically scaling with area law. So for Floquet system, actually, if the system is thermalizing, it's not very interesting. Eventually, it will heat up to infinite temperature, and there's nothing interesting about it. However, as a wise man said once, in the long run, we're all dead, right? So maybe before we die, we might want to see some interesting physics. So one obvious way to avoid Floquet heating is actually to use many-body localization. So it's well known that in Floquet system, if you have a many-body localized system, if you have many-body localization, actually this will prevent the system to reach infinite temperature, and you can stabilize the time crystal. They're interesting. They're very beautiful, and reviews by Vedica and Norm about all the different types of time crystals. And there have been two recent papers from Google and from a Delft group about realizing an SMBL discrete time crystal. We're going to take a different route here. We're going to basically look at a prethermal time crystal, where we basically drive the system so hard, so fast actually, faster than the local energy scale of our Hamiltonian, which in our case is J0, is the spin-spin coupling, so that we can actually observe interesting physics before the system basically thermalizes at infinite temperature. And we can do so thanks to a theorem that was proven by these papers, that basically if you have a drive that is fast enough, actually you can describe the system after a transient period. The system basically pre-thermalizes and is described by an effective Hamiltonian to first order, and the effective temperature in this in this plateau here is set by the energy by the energy density of your initial state. So in a certain sense, it's a very interesting way to tune the temperature in a system that it's actually closed and doesn't have really a temperature by tuning the initial state. And we can do this, of course, at the end with some, after some pre-thermalization time, there will be a time scale where the system eventually heats up to infinite temperature and nothing, there are no features there. So what, here? Right, this doesn't work anymore.
Strip to the left of your screen that seems to have popped up.
Oop. That's weird. Right, okay, perfect. Thanks. That was the problem. So, so yeah, what we're going to do now is basically initialize different initial state and apply a Floquet drive. Make sure that we actually reach this thermal plateau where the system is effectively pre-thermalized to and is described by this effective Hamiltonian, and then eventually we'll also observe that the system heats up to infinite temperature. So this is our drive. We basically have a perfect pi pulse, as perfect as we can do it in the lab, and then we apply this long-range Hamiltonian with mixed transverse field, both in y and z direction. So the effective Hamiltonian, if this works, the effective pre-thermal Hamiltonian is actually this transverse field IZ model. And so to make sure that we actually are in the pre-thermal regime, we prepare this specific initial state where we have the two, so everything here is polarized in X in the basically ordered direction, a ferromagnetic direction of this Hamiltonian, although the Hamiltonian is antiferromagnetic. And we prepare these two central spins in the Z direction, okay? And then what we see is that after roughly 3 times J, we reach these two spins basically reach the same value of the neighboring orange spin, of the neighboring spins, and this happens before the heating timescales. And we characterize the heating timescales by looking at the energy density, how it evolves in time and how it converges to basically infinite temperature. So we can measure the energy. It's just 2-body and 1-body correlators, and we see how it behaves as a function of our drive frequency. So we drive faster and faster, and we see that basically this decay, it doesn't, in principle, it should be exponential, but of course we have decoherence. So, but the trend is qualitatively what we expect. So the faster we drive, the longest is the heating time, both for a low energy nil state, where we have an antiferromagnetic initial product state, and for the high energy polarized state. High energy because the Hamiltonian is antiferromagnetic. So now, even if in the original Floquet evolution, there is not such a symmetry, what is interesting is that there is an emergent symmetry in the effective Hamiltonian. So we have this parity symmetry here. And so this global magnetization is a good parameter for the prethermal to discriminate between whether we have a prethermal time crystal or not. And this is basically the main result of the paper. If we start from a polarized high energy, in this case, you can think about it having a very low, very high negative temperature. We see that the system depends on the frequency. So the faster we drive, the more this time crystal survives, basically. Whereas if we start from the antiferromagnetic state, which is low energy but high temperature, high positive temperature, we see that the system collapses fairly quickly before the prethermal time. And so here, this is summarizing this plot here, where we have both the heating scale as a function of energy density and also the prethermal times, so the decays of these curves. All right, so that's the prethermal time crystal. I'll switch gears now, and I'll talk about another experiment, which relates to a few talks that have been mainly to the talk of Frank Polman. So basically, if we think about how many-body localization came up, at least in my understanding, is basically people starting questioning, if you have an Anderson localized system, which is non-interacting but disordered, and you add interaction, then you can get MBL. And so people recently started thinking, well, there is another way to localize non-interacting particles, which is basically apply a strong gradient, so to have Barnier-Stark localization. Then what happens if you have interactions in this system where you have a strong gradient? Would you have a so-called Stark MBL? And so there have been a number of theory work, and we heard on Monday about the cold atom experiment, where basically this is a Fermi-Hubbard model with a strong tilt, and they were seeing some signature of, let's say, fragmentation or Stark MBL. And so in our case, we're going to do it with ions, where basically the experimental procedures, it's fairly simple. We prepare an initial state that can be a nil state or a fully polarized state, depending on what energy density we want. And then we quench with our long-range Hamiltonian, and we apply a gradient. And we can tune the strength of this gradient. And basically then we measure both the individual magnetization to see if the state is, the memory of the initial state is preserved, or we measure the imbalance, so basically how many spin up and the difference between spin up and spin down, depending on which initialization we have, survives over time. So as you might expect, if we have no gradient or very small gradient, the system starting from a nil state thermalizes fairly fast. If we apply a very strong gradient, actually it stays, it retains the memory of the initial state. So we see that basically increasing the gradient, we have a steady state imbalance that grows as a function of G. And we can also look at what happens if we basically vary the strength of the gradient. And we did this for different initial states, right? Because you want basically the same behavior. If it's really Stark MBL, you want to prove that this is not something, for example, like scars that thermalizes very slowly, but those are very specific states. So we tried three different, very different initial states, and we see roughly the same behavior in the steady state imbalance at long times. And also we varied the gradient, and we investigated two different sides. We pushed our system to 25, which is okay, but it's not 50. But there are some technical problems that I can go more into detail. But yeah, and we see that the localization basically persists also for up to 25 spins. So that's the largest that we can go. Interestingly, we can also, we're not, since we have control of what kind of potential we can put on the system, we're not constrained to just study gradients. And we can, for example, apply a quadratic potential and see what happens. And in this case, we see that there is if you fine tune basically the maximum G over J, there are some regime where the center thermalize, but basically the edge of the system are still retains memory of the initial state. So this is, here is a, a plot of all the different spins. This has been done with 15 spins. So as an outlook, there are open questions. Of course, this is a finite size system. So we don't know if MBL is really more robust to how basically Stark MBL survives if we decrease alpha more and more. It's well known that if you decrease alpha and you have longer and longer range interactions, you will have, eventually will destroy MBL. And so we can use the gradient, for example, to explore quadrupole conservation. So we've seen on Monday that basically having a strong gradient is associated to having an effective dipole conservation. But if you have a quadratic potential, maybe you can think about conserving also quadrupole and higher moments. And maybe Stark MBL can be used to avoid Floquet heating in the same fashion as many body localization can be used for this purpose. All right. So now all these results. So there are also other results that I didn't cover, like for example QAOA and confinement, have been achieved with basically shining two Raman beams that are global, so it's a global interaction control, and using only one set of normal modes. So at Rice, what we're building right now, it's a high optical access experimental apparatus that allows us to both control the interactions locally and also to couple to different normal modes to explore more Hamiltonians. And I want to talk a little bit about what happens if you now open the system to dissipation, and instead of looking just at unitary dynamics, you basically look at dissipative many-body system. So broadly speaking, if you have a quantum system described by unitary and a pure state, if you have an environment, you can have basically information that leaks in, or you can have also, in principle, the back action of the environment on the quantum system itself. So I'm gonna basically give a very broad classification. So most of the results can be, or most of the systems that include dissipation can be cast in this form with the so-called Lindblad equation, where you have your coherent evolution and you have a jump operator that is basically a function of your density matrix. And what you look for to discriminate between different phases are basically properties of the average state. So you take an observable and you basically trace it with the density matrix. And in the talk of Ehud Altman, he said that there is nothing interesting here, but I don't really agree. I hope I can convince you that there is something interesting. And recently, there has been a different paradigm, in a certain sense, in how you can look at this dissipative system, where you basically have you interleave unitary evolution with measurements or dissipative operations. And people have found, as we've seen in the talk of Ehud Altman, that you have a measurement-induced phase transition. So basically, if you look at observable, they are non-linear with respect to the density, to the reduced density matrix, like for example the entanglement entropy, you actually can spot this measurement-induced phase transition. So the entanglement entropy, depending on how frequently you measure, transitions from volume law to area law. So, and this is a non-exhaustive list of papers about this topic. So what we asked then is, how can we observe this experimentally? So in principle, we have in the trapped ion toolbox, we can induce, we can extend the Floquet paradigm that we used before. Okay, 5 minutes, perfect. So we can extend the paradigm that we had before, and we can basically apply, rotations. We can apply interactions to create entanglement, and we can also interleave these operations with local dissipation, where, for example, we can either measure the spin or we can simply reset it with optical pumping. So basically, these two are just rotations. This is a kicked spin IZ model where you apply subsequent rotation and interactions, where this is long-range interactions. And then you also apply Krauss operators, where with a certain probability p, you reset your spin, and with 1 over p, which you can interpret p as the fraction of qubits that are actually reset. So this is, I think, an interesting question, because most of the models, I mean, not all of them, but most of the models have looked at Clifford gates, where you can actually simulate the system for large system size. There is a number of works about Hamiltonian evolution interleaved with dissipation, but definitely this one has not been studied yet. So basically, this is a summary of what we found. We found that there are, for this long-range Hamiltonian, we studied what happens as a function of alpha. There is both a dissipative phase transition if you look at average observable, and this is just symmetry breaking order-disordered ferromagnetic phase transition. You can detect it by just looking at two-body correlator or higher-order correlators. Or if you actually are good enough experimentally to detect entanglement entropy, you can actually see a measurement-induced phase transition. And there is also a region where the two overlap. You have both, the two transitions are not related, but you have both a volume law, area law, and also a symmetry breaking dissipative phase transition. So, for the dissipative symmetry breaking phase transition, we can do the cluster mean field, and it's basically analytic for alpha equals 0. And with the binder cumulant, we're pretty sure that there is a transition at fairly large p, and we can extend this to a fairly large system size. If we do the exact generalization for alpha greater than 0, we actually see we can do the same. Of course, we're limited by our computing power, so we go up to 24. But most interestingly, we can look at what happens at the critical p, where the system basically develops ferromagnetic order, where it's a paramagnet. And we see that, for the system size that we have, for alpha roughly 1.3, the transition basically dies. So for the measurement-induced phase transition, we looked at the quantum mutual information. So we did finite size scaling to actually locate the PC, the critical p at which the transition occurs. And what I want to show is basically the comparison between how PC for the measurement-induced phase transition and for the dissipative phase transition varies as a function of alpha. And as you see, the trend is opposite. So for shorter and shorter range, the measurement-induced phase transition is more robust, whereas for shorter range, the dissipative phase transition dies out. And this has interesting implication also in terms of the region where the two transitions coexist. And so, for example, if you have both volume law and antiferromagnetic and ferromagnetic order, actually there is some signature that this affects how much volume law is your wave function. So the wave function doesn't really spread out in Hilbert space, but is more it has more weight on the ferromagnetic sector in a certain sense. So in terms of experimental consideration for this dissipative phase transition, I mean, we can go more into the details, but basically with optical pumping, we can reset the spin with negligible crosstalk. After a few photons, spins are basically down. And we don't need to do any post-selection in this case. For the measurement-induced phase transition, there are a number of challenges. We have to detect an observable that is non-linear in the reduced density matrix. We have to post-select over quantum trajectories, as we've seen in the talk of Ehud Altman. This means that once we measure, we only want to average when we get the same measurement outcome, and this creates an additional exponential overhead on the number of measurements that you have to do in general. And then we also have to detect individual qubit with negligible crosstalks. So very quickly, the way that we address all these challenges ideally is, first of all, there is this nice paper by Mike Gallants that says that if you have an ancilla and you entangle the ancilla before the protocol, you can actually measure only the entanglement entropy of the ancilla, which is much less daunting than measurement entanglement entropy itself. On the other end, this exponential scaling becomes more manageable, especially because we can tune alpha. So if we tune alpha to 0.5, PC is actually a small number, and this exponential scaling is not so unmanageable anymore. And finally, to perform individual measurements, we can actually hide the amplitude of each qubit that we don't want to reset or measure to an alternative clock state, and there is this beautiful paper that demonstrates this mapping that you can do back and forth. So in principle, all the ingredients are there. So I don't have time probably to mention other, to go more in details, but there is also other directions we're working on at RISE, thinking about how we can implement, use trapped ion to implement high energy and lattice gauge theories. These references are basically, if you're more interested. So I'm collaborating with Kaden on basically the interface of quantum spin glass and variational optimization. And on the more applied side, I have a project with a company and with Norbert Linke on how to make ion trapping easy by building a trap that is plug and play. So I guess it's not particularly interesting for this audience, but so here is a picture of the lab. It's not like that. Now it looks more like that, luckily. And it's been 1 year that we've been in the lab, and we have already the vacuum system. We have the trap assembled. We characterize the atomic source. So we're steadily going towards trapping and having possibility to do experiments. With this, I would like to acknowledge my former team, my former PI, Chris, and also Will, who's been the driving force on the previous 2 experiments, and of course, all the grad students, and last but not least, my current team and all my collaborators. Thank you very much.
I don't know, maybe it's more question to Sirius. I don't understand how you can distinguish Stark MBL and Floquet, because it's like knowing from electromagnetism, electric field is equivalent to time derivative of vector potential. If you want, I can go to rotating frame, electric field is gone, and I have hopping which oscillates in time. So you're either forced to say that both Floquet and electric field lead to slow heating or thermalization, or you're forced to say that both don't lead to heating. But it just cannot be that one is absolute statement and say one localizes, one doesn't. It's just impossible, because they are completely equivalent problems.
I never thought about
so
this.
If you think, I mean, well, just electric field is equivalent, so we can say it's time derivative of vector potential. If you just oscillate hopping in time with frequency, which is electric field, then this is Floquet problem with time-dependent hopping. So it's completely equivalent, like 100% equivalent to a problem where you have non-oscillating system in electric field.
I see. So
they're just identical.
Okay. So you're saying that if the Floquet system is
prethermal,
prethermal,
Stark and belay also has to slowly heat. Oh well, yeah. So
okay. Well, yeah. I don't have a counter argument against that. I think it's an open question whether probably not for you, but whether Stark and
there could be always exceptions.
Yeah. I don't know. But that's a good parallel.
Can you hear me?
Yeah, I can. I don't know if.
Yeah. Okay. Okay. Now, very nice talk. I have 2 short questions. So for the Floquet, you had a BY term and a BC term, and then the BC term disappeared. What is the role of the BC field?
So the BC field is to basically break to break the symmetries, to not have that symmetry, the emergent symmetry, so that we can actually say that that's not present in the Floquet Hamiltonian, and it's present in the.
But in the effective Hamiltonian, it disappears. Yes?
Yeah, exactly. Yes.
But in the experiment, you have both.
Yes, we have both. Yes.
And my quick question is for the second part, for the Stark localization. So in principle, you have sigma S, sigma X, and the
gradient.
And the gradient. But sigma x is not only hopping, but have the sigma plus term too. So what is the role of this sigma plus?
Yes,
sigma
so for strong gradient, that's sigma plus. I mean, locally, you have high electric field, except maybe for the first edge, but basically you can think about it that, you know, those terms are suppressed because the local magnetic fields is very high. So the sigma plus, and sigma minus are basically suppressed in the region where the gradient is large.
But when it's small, it's not necessary. Where the gradient is small, maybe these other terms should play a role.
Yes, that's true. Yes, but
okay.
Yeah, I'm not sure if that's if that is a problem for Stark MBL or not to have that sigma.
Because you want to go to the strong.
To the strong gradient. I guess for large gradient, only the edge is in the low regime. If we have, so most of the system will be in the XY model regime, where you have a strong local magnetic field along Z. So.
So, but you have a uniform field too? No,
we apply
only the gradient.
Field. And the reason is practical, because once you actually it's in one of your papers that when you have a strong magnetic field that becomes comparable to the tuning, then you start to have catastrophic effect in the fidelity.
Okay.
So that's the reason why we cannot push it, you know, too large system size, because eventually the gradient on the edge will become of the same order of the tuning, and then from the motional modes, and then basically we will not have a good fidelity in the XY model.
Okay.
Dave Weiss, did you want to ask?
Yeah, so for the Stark MBL, is it possible to reformulate this this localization that you get as being due to something like an energy barrier, right? That is, when there's this large gradient in some part of the system, it's hard for the system to leave that local place because it's not energetically allowed, or at least, you know, there's some incredibly long
So this one, I actually have a backup slide on this. so this would be the picture of basically non-interacting, right? That basically you're tilting the system so much that somehow, you know, you're energetically suppressed to go anywhere, right? But the idea, so in the paper, we try to, you know, detect the effect of the interaction with the so-called DEAR protocol. I'm not sure if you can see the slides.
I can see the slides now, yeah.
So basically what we do, we do this Ramsey protocol where we compare these two sequences. We have, you know, we have a reference spin, and we apply pi/2, then we apply just for half time the interaction, and then we apply spin echo, and then we reverse, you know, as you see in the picture, we apply again the interaction Hamiltonian, and then final pi pulse. So if we want to single out the effect of the interaction, we can add pi/2 pulses on the neighboring spins, and we can do this for, you know, for different regions and different distances from the reference spin. So in this protocol, actually you will have that, you know, the non-interacting Anderson localization, since it's not related to what these other spins are doing in a certain sense, but it's just related to disorder. And also in the thermal regime, these two curves will give you the same effect. And in our case, I mean, the signature is there. Is basically if we do these two protocols, we do see a difference, and this difference is due to the fact that there is also an interaction with the rest of the system. So it's not only you know, a naive non-interacting localization where the system cannot go to.
So the difference that you're pointing to is the difference between that blue and that green curve?
The, yeah, like dark green.
Right,
and, yeah.
Looks kind of blue and green for me. I agree the colors are messed up.
Okay.
But,
yeah, and we did this for different, you know, it's small, but it's still statistically significant. Of course, if you take a region of spins that is too far away, then it, you know, it goes to 0. But at least for you know, 2 spins distance, it's it's sizable, and also for as a function of gradient, it behaves according to the theory. So it is something related to the fact that the system has also interactions.
I see. I mean, I guess I'm a slightly unconvinced, but you know, that's neither here nor there. Just because you're doing two different things in the experiment, and then that there would be a slight shift in a probe signal is not in itself surprising. You know, it would be nice if you could sort of turn on and off something so that, you know, it's really the difference between localized and not localized.
Well, in a certain sense, we do turn on and off these two, right? This fiber two.
Yeah, I know, but I'm saying, well, okay. But then the signature of the change is
basically that, you know, if everything is local, you basically echo out everything. If everything is not interacting, these two will be, this fiber 2 here will not contribute to what's happening to this reference qubit. But in MBL, actually, you can single out the fact that there is basically an interaction between this region and the rest.
I see. So you're saying that there is an interaction, and the fact of that interaction is what, you know, not having the interaction or having the interaction is the difference between localization and not being localized?
Yeah, between MBL and non-interacting localization.
Okay. I wish I were there.
Yeah.
Sort it out.
So next time you come to the KITP, you can finish that discussion. Varun?
Hi. Yeah, thank you. I think I should maybe first read your paper, but I had just a stupid question. So just to make sure, you have a transition in the average density matrix itself, right?
Oh yeah.
So if I unravel this density matrix into individual quantum trajectories, is there a measurement induced transition in those individual trajectories across your paramagnet area to paramagnet volume? Are all of those trajectories individually having this measurement induced transition, if I think of the average density matrix as sum of density matrix of individual trajectories? Or
so I'm not sure I understand the question, but yeah, in the measurement induced phase transition, we do look at individual trajectories.
Right, but I'm saying, let's say I take your mixed state evolution, which, let's say, from 1 to 4.
Okay.
Phase 1 to phase 4, there is a phase transition in the mixed state, which is evolved by some Lindblad equation, right?
Yeah, exactly.
So now I can quote unquote unravel this Lindblad density matrix into infinite number of
yes.
quantum trajectories. Let's say I pick one of these quantum trajectories.
Yes.
Is there a transition in that quantum trajectory, which is now will require post-selection and so on, like the usual measurement?
Yeah. This is exactly the MIPT. What we do is exactly that. Like we always, you know, in the numerics, we always keep track of all the quantum trajectory. If we want
right. No, I understand. But I'm saying, is the MIPT occurring exactly when 1 to 4 transition occurs also? Is there?
There is a region where they both occur.
I see, but they don't coincide. I'm trying to.
No, exactly. That's the point. That's one of the point of the papers. They don't coincide, and they have very different behavior. But also they don't coincide, but they also influence each other. Because, for example, when you have coexistence of both volume law and ferromagnetic order, you can see in the participation entropy. Actually, I have a backup slide for this too. You can see that basically in the long range case, this one, if it was really volume law, should be log 2, and is not, and it's closer to log 2, a little bit more closer. Of course, these are finite size in the volume law when alpha is equal to 2. So the take-home message is also that if you have volume law and ferromagnetic order, somehow your delocalization in Hilbert space is more limited, and because your wave function is not spread out, but it has more weight on the ferromagnetic part of the Hilbert space. So the two transitions do not coincide. They have different behavior in terms of PC, etc. But they do influence each other in a certain sense.
And just to make sure, when you say it's a volume law phase for the average density matrix, you are just looking at trace of rho log rho for the whole system.
No, when I say volume law, I only talk about the
mutual information.
the entanglement entropy. Yes.
What do you mean entanglement entropy? The mutual.
Yeah, the mutual information. Or yes, I mean, and also the scaling of entanglement entropy.
But did you look at any more mixed state measure? I mean, actual entanglement, like negativity or something like that, or?
We looked at the purity also. There is an appendix in the paper that basically looked at how the.
But I meant some actual entanglement measure, not like purity or mutual information, something like negativity, like in Woodstock.
No, we didn't look at negativity.
Great. I see. Okay. Yeah. Thank you.
Ehud, can you use a microphone? So I can bring.
Yeah, maybe I missed, but in the measurement-induced transition, you're in the mixed state, or not? It's not a mixed state, right?
No.
You're unraveling it.
No, we are unraveling it. Yes.
Yeah. Okay.
Yes.
Okay. So I don't think you need negativity in this case.
I know. I just to make sure, I was asking about the average density matrix transition when I asked about negativity, not the MIPT.
Oh, I see. No, we haven't looked at that. We haven't looked at the negativity of the mixed state.
Yeah,
no.
So in the, I don't think, okay, we can talk about it, but I think in that case, there would not be any negativity probably because it's coupled to an infinite bath.
Yeah, I would expect the same. I mean, this basically stems from basically me thinking that at the beginning that you can observe measurement-induced phase transition by resetting, but actually you're erasing information when you reset. So if you don't keep track of what are the states before the resetting, then you will end up somehow destroying entanglement, right? Because you're coupling to a bath. So yeah.
Great. I think in light of the time, we should wrap up the discussion there. So let's thank both of our speakers.